recording going. Okay, so we're going to open up FinRel here, 3 underbar FinRel. And here we're going to be talking about another sort of category with sets, another sort of category whose objects are actually the same old objects we just saw in FinSet. But what distinguishes this category is what the morphisms mean, like how we interpret a morphism, how it acts. And the morphisms here are relations between sets. So instead of being just a mapping where each element in the domain is mapped to a specific element in the codomain, what we're going to have is a relation between them, which is a much more sort of symmetric type of construct, right? Where a given element in the domain can be mapped to 0 or more, can be mapped to 1, to 2, to 3 different elements here. So 1 might go to A, C, and D, for example. 2 might go to none. 3 might go to C and B. And in a relation, you might take some delight, as I do, when reflecting on the fact that we could actually take a relation between X and Y and turn it into a relation from Y to X. It's symmetric in a way that a function generally is not. But here, we're going to be able, like in the category of sets and functions, the category of sets and relations will have some common themes. We're going to be able to think about preimage. We're going to be able to ask questions about these relations. We're going to be able to compose the relations. We're going to have an identity relation, which relates each element, say, in X to the same element, right? Or each element in Y to the same element. Composing relations, though, will have a different flavor. If we go from X to Y, and we might have multiple things, for example, going into C, and then from Y onto Z, and we have multiple things from C to different things of different elements of Z. We can get to those elements of Z through C, but we could also get to them through A, because A might go to some of those things in Z. And I feel terrible I don't have a diagram to show this, but we get something more similar to matrix multiplication. We can get to from a thing in X to a thing in Z through many different ways of mapping to Y and onto Z. And we have to consider all these different paths by which we can get from X to Z through different intermediaries Y. So we have a different notion, although we have a notion of composition that has mathematical properties associated with a category, and although we have identity relations, the specifics of what it means to compose these relations, the flavor of it in terms of the elements is rather different. So I'm going to, having opened that up, making sure that Julia is loaded, I'm going to sort of run these, and I'm running through these components here. So first I'm going to define a relation, okay? And I flat-footedly call it relate. And this is going to be a relation between X and Y. So between sets X, which is going to be FinSet 6, so a set of whose elements are 1, 2, 3, 4, 5, 6, and FinSet 6. And the relation between a value X from first FinSet and a value Y from the second FinSet will exist. A relation between them will exist. They'll have a relation. They'll have this relationship. If X is less than or equal to Y. And this defines some relation. As you can imagine, the value 1 from this fin set would be related to 1 from the target fin set, 2 from the target fin set, 3 from the target fin set, but that's fine for relation. That wouldn't do for a function, but it will do here, right? By contrast, if X were 6, it would not have a relation with 1 because 6 is not less than or equal to 1 here. It would not have a relation with 2 or 3, only with 6, right? So I'm going to define that, and it knows about this as a relation, much as it knows about a fin function as a function. And I will say, and I stand, or I sit remiss here. I could have asked about the domain of this, and in FinRel, this is a FinRel 6. It is a finite set of size 6. I could have asked about its codomain. But I could also ask it here to map, for example, 3 and 2, and 2 and 3 for good measure. And for example, if we ask, is 3 related to 2? The answer is no, because 3 is not less than or equal to 2. But 2, by contrast, and that's why it's 0. But 2 is less than or equal to 3, and hence the 1 here. Okay. So we could ask about that. Forgive me, I don't know. I said we could do a pre-image, but I'm actually not completely sure about that. You may remember when we had fin sets here, and why is this being truculent? When we had fin sets here, we could ask for a pre-image of a function for 1 under that function, and it would tell us all things that mapped into that function. Like a pre-image for this, a B, would tell us 2 and 3. I want to just see, whether we can get a pre-image for, let's say 2. Here, I'm not actually sure it will tell us that. It may complain bitterly. No, we can't do a pre-image. So I can't do a pre-image, right? It's unhappy. Okay. Oh, well, okay, mumble. We'll have to see if we can do it. I don't think so. It looks like it's defined for sets of functions. I thought we could ask all things related. There's probably another way to do it. Okay, maybe one of my students could find out. Okay. One thing we could do is represent this as a matrix, right? We know for X and Y, whether they're related or not. Gosh, we should be able to relate this. And indeed, at a deep level, these things are tightly connected. FinRel is tightly connected with Boolean matrices, or Boolean rigs, where rigs are rings without negative, also called semi-rings, without a negative operation. And we could show it as a matrix. So we can say, hey, show me this relation between X and Y as a matrix. And there should be some nice way to show this in a nice square form as a matrix. Again, maybe one of my students could find me a nice way to show it as a nice little matrix, in tidy columns and rows. But this isn't bad. So like, we're going to be able to characterize successive rows of it, and you can see there's successive structure in those rows, with the first one only having 1 true, the second having 1 and 1, second having true and true. So 2 is less than or equal to 1 and 2, true, true, true for the next, etc. We can also define a relation, another relation in terms of its matrix of things that are related. And we're doing so here. This is not the same relation, but we're just defining a different relation. We could define it kind of symbolically, if you can call it that here, with a bit of code, or we can define it in terms of a matrix. Okay. Okay, well, So that's kind of nice. Well, define well, really, it's a third relation by all justification. Let's define this. Okay, here's a fin relation. X plus y mod 3 is equal to 0. What can we do? Well, we can express it as a matrix. But here's a really nifty thing. You've probably been waiting for it, some of you. We can compose the two. We can compose our first relation up here, which goes from kind of conceptually from a set of size 6 to a set of size 6. And we can compose that to our new relation, goes from a set of size 6 to, well, a set of size 6. I'm not very creative here. And we can get out a new relation, and we can present it as a nice little matrix of Booleans in a Boolean ring. We can also, for those interested in going deeper, define like meets between these things. So if two relations are RLT and R sub mod 3, if there are two relations, we can take their meet, which requires both be true, for it to be true. Or we can print out the result, or we could take their join. The first is equivalent, or we're taking their and, right? Here we're taking their or, and we can find that and get another relation. So we're deriving relations from other relations, from pairs of relations. Okay, so that was FinRel. So once again, we have, and you can put this title aside, but we have objects. Those are these sets of finite sets of a certain size. Here we have this odd proclivity for 6, but it's nothing privileging it. We have these morphisms here, and these morphisms here are relations between this set and this set. And there's an identity one that relates any set to itself. So 1 to 1, 2 to 2, 3 to 3, or whatever. And each of the elements to that same element. And we can compose these relations in a kind of, I said, sort of matrix-like way, though leaving it for you to think about. And you get a relation out, right? And we can do more. We could think about taking meets and joins, etc. So these have the smell of categories to them. These are set-like categories, which are recommended by these features. They have these object sets. They have these morphisms, which these functions on the one hand, or relations in the other. They can be composed. They have identities. Each one has an identity. But more than that, and I haven't shown this, but there's unitality. So if you compose a relation with an identity relation, a relation R with an identity relation, you get R back. And the same thing with identity relation and R. Same thing with a function. You compose an identity function with any function f, you get f back in either order. And so they observe unitality. They honor the unit in their composition. But more than that, they're associative. So I'm not going to prove this by any means, but if we compose functions f and g and then h, it's the same as composing f and then g and then h. And the same thing is true with relations. You have this nice associativity property. They're yearning to be recognized as full categories. And that is where we're going next, with your leave. Okay, so I'm going to stop.